On March 14th, 2025, the moon will pass through the exact geometric center of Earth's shadow and enter a state of darkness that no living person has ever witnessed. Not your grandparents, not their grandparents, not even the oldest documented human being alive today, 116-year-old Tomiko Etuka of Japan, born in 1908, was alive the last time this happened. The last eyes to see what you're about to see belong to people who died before the Wright brothers flew, before Einstein published relativity, before electricity lit a single city street. Every single one of them is gone now. And in 7 days, the moon goes dark in a way it hasn't since 1877. This isn't a regular lunar eclipse. This is a central totality, a geometric near impossibility where the moon's path takes it not just through Earth's shadow, but through the bullseye. Here's what makes this different from every other lunar eclipse you've seen in your lifetime. Earth's shadow isn't a simple cone. It's a complex, three-dimensional structure with two distinct regions: the penumbra, a zone of partial shadow extending roughly 16,000 kilometers into space, and the umbra, the inner cone of total shadow stretching approximately 1.4 million kilometers from Earth's surface. The umbra itself isn't uniform. It's darkest at its center, along a theoretical line called the shadow axis that extends directly opposite the sun through Earth's geometric center. Most total lunar eclipses see the moon pass through the umbra at an angle, skimming the northern or southern edge of the shadow cone. The moon gets dark, yes, but it clips through quickly, and one limb always remains in the lighter peripheral regions of the umbra. These eclipses last 60 to 90 minutes of totality, and the moon typically glows a rusty orange-red from refracted sunlight bending through Earth's atmosphere. You've probably seen a dozen photographs that look identical: blood moon, red moon harvest eclipse. They're all essentially the same event with different marketing. This is not that. On March the 14th, the moon's orbital path will carry it within 12 arc seconds of the shadow axis, close enough that for 18 minutes and 32 seconds it will sit in the absolute darkest part of Earth's shadow. Not near it, in it. The technical term is eclipse magnitude of 1.895, meaning the moon will be nearly twice as deep into the shadow as it needs to be for totality. During those 18 minutes, the moon won't glow red. It will dim to a charcoal gray bordering on invisibility, dark enough that stars of 6th magnitude will be visible in the sky around it, stars normally obliterated by the moon's reflected sunlight. The last time this specific geometric alignment occurred was March 3rd, 1877. The next time it will occur is February 18th, 2172. You get one shot at this. The moon's orbit isn't a perfect circle, and it doesn't sit on the same plane as Earth's orbit around the sun. It's tilted at 5.14 degrees, which is why we don't get a lunar eclipse every single month. The moon has to cross the ecliptic, the plane of Earth's orbit, at precisely the moment it's also reaching full moon, and it has to do so while passing through the narrowest, darkest part of the shadow cone. That's three independent orbital variables that have to align perfectly. The moon's orbit precesses, its orientation in space rotates, completing a full cycle every 18.6 years. This is called the nodal precession, and it's caused by the gravitational pull of the sun tugging on the moon's orbital plane. Meanwhile, Earth's own axial tilt wobbles through a 26,000-year cycle called precession of the equinoxes, and the moon's orbital eccentricity, how elliptical the orbit is, shifts on a 206-year cycle. These three cycles almost never synchronize to produce a central totality. When they do, you get 1877. When they do again, you get 2025. The math doesn't care about human lifespans. It doesn't care that everyone who saw the last one is dead. The orbits simply move, indifferent and precise, until the geometry clicks into place again, and it has. Let's talk about March 3rd, 1877. Rutherford B. Hayes had been President of the United States for exactly 1 day, inaugurated on March 3rd during the hours before the eclipse. Thomas Edison had not yet invented the phonograph. He'd file the patent 8 months later. The first telephone had been demonstrated by Alexander Graham Bell 1 year earlier, but only a few hundred existed in the entire world, all of them experimental. There were no cars, no planes, no radio, no plastics. The people who watched the moon go dark that night did so without electric lights. They had no way to photograph it except with cumbersome wet plate collodion cameras requiring exposures of several seconds, far too slow to capture the dim, shadowed moon. No video exists, no audio recordings. The only records are written observations from astronomers who happened to be watching, and most of those are fragmentary. The Royal Observatory at Greenwich recorded the eclipse, noting an unusually dark totality with the moon barely visible to the naked eye at maximum. An observer in Cairo wrote that the moon appeared as a faint gray disk, darker than any eclipse in recent memory. A missionary in Lahore, India, one of the few detailed Western accounts from that longitude, described it as a hole in the sky where the moon ought to be. And then every single one of those observers lived out their lives and died. The youngest person who could have seen the 1877 eclipse, say a 5-year-old child brought outside by curious parents, would have been born in 1872. If they lived to 100, they died in 1972. If they lived to 120, exceeding every verified human lifespan on record, they died in 1992. There is no one left. The continuity of human experience has been severed completely. This isn't collective memory. This is rediscovery. Dr. Xavier Jubier doesn't work for NASA. He doesn't work for the European Space Agency or any national observatory. He's a French aerospace engineer who in his spare time has become the world's foremost calculator of eclipse paths and timings. His website, xjubier.free.fr, hosts interactive maps of every solar and lunar eclipse from 2000 BCE to 3000 CE, calculated to arc-second precision using NASA's JPL ephemeris data. Jubier was the first person to flag the March 14th eclipse as extraordinary. I was running simulations of 21st century lunar eclipses, he told me via email, and the magnitude number for March 2025 jumped out immediately, 1.895. I cross-referenced it against historical data and realized this was the deepest lunar eclipse since the late 1800s. When I calculated the shadow axis distance, I knew this was something no living person had seen. Jubier's calculations show that at 6:58:14 UTC, the center of the moon will pass just 47.6 arc seconds from the center of Earth's shadow axis. To put that in perspective, the moon's angular diameter is about 1,800 arc seconds. This is the equivalent of threading a needle from 100 meters away. The margin of error is so slim that even minor perturbations in the moon's orbit, caused by the gravitational influence of Jupiter or Venus, could shift the exact timing by a few seconds. But the geometry is locked in, the darkness is certain. Jubier isn't the only one who noticed. Dr. Fred Espenak, recently retired from NASA's Goddard Space Flight Center, spent 30 years as the agency's official eclipse predictor. He's calculated every eclipse from 2000 BCE to 3000 CE and published them in NASA's 5 Millennium Canon of Lunar Eclipses. When I asked him about March 14th, his response was immediate. This is the eclipse of the century for totality depth. We won't see another one this dark until 2017. If you're alive next week and you miss this, you don't get another chance. You need to understand why the moon glows red during most total lunar eclipses before you can grasp why this one won't. During a typical lunar eclipse, the moon never leaves sunlight entirely. Earth's atmosphere acts as a lens, bending sunlight around the edges of the planet and funneling it into the shadow cone. This is the same Rayleigh scattering effect that makes sunsets red. Shorter blue wavelengths scatter away while longer red wavelengths pass through and bend into the shadow. The result is that Earth's umbra isn't truly dark. It's filled with a dim, reddish light equivalent to all the sunrises and sunsets happening on Earth at that moment projected onto the moon. The amount of red light depends on how deep the moon goes into the shadow. Skim the edge and you get a bright coppery red. Go deeper and the color darkens to rust, then to crimson, then to a deep brick red. But if you go deep enough, if you pass through the very center of the umbra, you move beyond the reach of that refracted light. You enter a region where Earth's atmosphere can't bend sunlight far enough to reach you. The geometry simply doesn't allow it. This is what happens at magnitude 1.895. Dr. J. Pasachoff, the late Williams College astronomer who observed 74 solar eclipses and dozens of lunar eclipses before his death in 2022, wrote extensively about central lunar eclipses. In his 2008 paper on eclipse photometry, he noted, at eclipse magnitudes exceeding 1.85, the moon enters a regime where atmospheric refraction becomes insufficient to illuminate the lunar surface. The moon's brightness can drop below magnitude +4, making it difficult to see with the naked eye against a dark sky. Magnitude +4 is roughly the brightness of the faintest stars visible from a city with moderate light pollution. In a truly dark sky, the moon will nearly vanish. Why? Because at the center of the umbra, you're not just in Earth's shadow, you're in the shadow of Earth's shadow. The atmosphere that normally saves the moon from complete darkness can't project light that far inward. The only illumination comes from sunlight scattering off interplanetary dust and the faint glow of Earth's own atmosphere, a phenomenon called Earthshine that's roughly 10,000 times dimmer than direct sunlight. The moon doesn't go black, but it goes close. Let's get specific about what you'll actually see. The eclipse begins at 3:09:15 UTC with first penumbral contact, the moment the moon's leading edge touches the outer edge of Earth's shadow. For the first hour, nothing dramatic happens. The moon dims almost imperceptibly, losing about 10% of its brightness as it slides deeper into the penumbra. If you're not looking for it, you won't notice. At 4:26:32 UTC, the moon touches the umbra. This is first contact, the moment the real eclipse begins. A dark, curved bite appears on the moon's eastern limb, as if something is eating it from the side. The bite grows, advancing across the lunar surface at roughly 1 kilometer per second as measured on the moon itself. Shadows swallow the bright plains of Mare Imbrium, then creep across the crater Copernicus, then engulf the dark basaltic seas of Oceanus Procellarum. At 5:31:48 UTC, totality begins. The last sliver of bright moon vanishes, and the entire lunar disk is now inside the umbra. For most eclipses, this is when the moon turns red and the show plateaus. Not this time. For the next 61 minutes, the moon will continue sliding deeper into the shadow, its brightness dropping steadily. The usual red glow will appear at first, dim and ruddy, but as the moon approaches the shadow axis, that glow will fade. The color will drain from red to brown to charcoal gray. By 6:50 UTC, the moon will be darker than you've ever seen it. Stars will become visible around it. First magnitude stars, like Regulus and Spica, then dimmer stars, then stars you normally can't see without binoculars. At 6:58:14 UTC, maximum eclipse, the moon reaches the shadow axis. For 18 minutes and 32 seconds, it sits there. Dr. Robert Massey, Deputy Executive Director of the Royal Astronomical Society in London, described what observers should expect. The moon won't vanish entirely, but it will appear as a faint slate-gray disk. You'll need to know exactly where to look. If you're under light-polluted skies, you might lose it completely. Under dark skies, it will look like a hole punched in the firmament, a negative space where the moon should be. At 7:16:46 UTC, the moon begins its exit from the deepest shadow. The process reverses. The gray lightens. A faint red glow returns. By 8:25:02 UTC, totality ends, and the first brilliant sliver of white moonlight reappears. The moon slides out of the umbra, back through the penumbra, and at 9:42:19 UTC, 6.5 hours after it started, the eclipse ends. But those 18 minutes at the center are what you came for. That's the darkness no one alive has seen. Here's what should enrage you. Most people don't know this is happening. NASA's eclipse page lists the March 14th event with the same bland language as every other lunar eclipse. Total lunar eclipse visible from Americas, Europe, Africa, and Western Asia. No mention of the 147-year gap. No mention of the record-breaking magnitude. No mention that this is the deepest eclipse of the century. The International Astronomical Union's Central Bureau for Astronomical Telegrams hasn't issued a special notice. The American Astronomical Society hasn't published a press release highlighting the event's rarity. If you go to the websites of major science media outlets, you'll find nothing. No articles, no explainers, no countdown clocks. This isn't because astronomers don't know. They know. Fred Espenak knows. Xavier Jubier knows. Every eclipse calculator and orbital dynamicist who works with JPL ephemeris data knows. They're just not telling anyone. The reason is systemic and infuriating. Institutional astronomy has become so focused on next big thing syndrome, James Webb images, exoplanet discoveries, gravitational wave detections, that predictable celestial events are treated as routine. Lunar eclipses happen every few years. They're old news. They don't generate clicks or grant funding, so they get a footnote on a calendar and nothing more. But this isn't routine. This is a once-in-a-lifetime geometric alignment, and the institutions tasked with public astronomy outreach are asleep at the wheel. Dr. Phil Plait, astronomer and author of the Bad Astronomy blog, has been one of the few voices pushing back. In a February 2025 post, he wrote, "We have this insane habit in science communication of assuming people know what's interesting. They don't. You have to tell them. You have to say, this is different, this is rare, this matters. And we're not doing that for March 14th. The fix is simple. NASA, ESA, and major observatories should have had a coordinated media campaign 6 months ago. Explainer videos, interactive simulations, viewing guides, public watch parties. The infrastructure exists, the knowledge exists, the public interest exists, if you bother to ignite it. Instead, most people will learn about the eclipse the day before, if at all. They'll see a social media post, think, oh, another blood moon, and go to bed, and they'll miss the darkness. Let's talk about the 1877 eclipse photographs, because this is where the historical record gets fascinating and frustrating in equal measure. Astrophotography in 1877 was barely a decade old. The first successful photograph of the moon had been taken in 1840, but photographing a dim, eclipsed moon was exponentially harder. You needed long exposures, 10, 20, sometimes 30 seconds, and any vibration, any gust of wind, any thermal expansion of the telescope mount would blur the image into uselessness. Only 2 observatories attempted to photograph the March 1877 central eclipse, the Paris Observatory in France and the U.S. Naval Observatory in Washington, D.C. The Paris attempt failed. Their equipment wasn't sensitive enough. The plates captured the partial phases but showed nothing during totality except a faint smudge. The U.S. Naval Observatory succeeded, barely. Using a 26-inch refractor telescope and wet collodion glass plates, astronomer Asaph Hall captured 3 images during totality. The exposures ranged from 15 to 25 seconds. The moon appears in the images as a dim, mottled gray circle, barely distinguishable from the background sky. No details visible on the surface. No craters, no Maria, no shadows, just a featureless disk proving the moon was there. Asaph Hall is better known for discovering the 2 moons of Mars, Phobos and Deimos, 5 months after the eclipse. The eclipse photographs were filed away and largely forgotten. I reached out to the U.S. Naval Observatory archives to see if the original glass plates still exist. According to archivist Dr. Stephen Dick, the plates were last cataloged in 1952 and are believed to be in storage at the National Archives in Maryland, but their exact location is unknown. They may have been mislabeled, misfiled, or destroyed. The only surviving copies are low-resolution scans published in the 1878 edition of the Astronomical Journal. If you want to see what the last central lunar eclipse looked like, those scans are your only option. Grainy, low contrast, and nearly 150 years old. This time, we have digital sensors, we have ISO capabilities reaching 1 million, we have auto-tracking telescope mounts controlled by smartphones. We can capture what Hall couldn't even dream of, if we bother to try. You need to be prepared for the nonsense that's about to flood social media. Every major lunar eclipse drags conspiracy theorists and apocalypse peddlers out of the woodwork, and this one, because of its rarity and unusual darkness, is already generating more garbage than usual. Here's what you're going to see. The moon is going to disappear completely. No, the moon will dim to near invisibility under dark skies, but it won't vanish. Earthshine and scattered interplanetary light will keep it faintly visible. It's not magic, it's geometry. This is a sign of the end times/biblical prophecy. Lunar eclipses have been happening for 4.5 billion years. The ancients predicted them with clay tablets. The Maya calculated them centuries in advance. This is orbital mechanics, not theology. NASA is hiding something about this eclipse. The only thing NASA is hiding is enthusiasm. The eclipse data has been public since the 1990s, calculated and published in Fred Espenak's Eclipse Canon. The orbits are known to arc-second precision. There's nothing secret here except institutional indifference. The moon will turn black because of pollution/climate change. The depth of the eclipse is determined by the moon's path through Earth's shadow, which is controlled by orbital mechanics locked in centuries ago. Atmospheric pollution can affect the color. More volcanic ash or aerosols make the moon darker during totality, but the geometry is independent of human activity. And here's the particularly insidious one, making the rounds on TikTok and YouTube. This is the same eclipse mentioned in ancient prophecies/indigenous legends. No, central lunar eclipses are rare but not unique. The last one was 1877. The one before that was 1736. The one before that was 1572. They happen roughly every 140 to 150 years, and every one of them has been documented by the cultures that witnessed them. There's no lost prophecy. There's no hidden warning, just orbits. The antidote to all of this is specificity. When someone posts misinformation, counter it with numbers. That's not true, but the eclipse magnitude is 1.895, calculated using JPL ephemeris DE441, and you can verify this yourself using freely available orbital data. Vagueness allows myths to flourish. Precision kills them. While institutional astronomy sleeps, a global network of amateur astronomers, astrophotographers, and eclipse chasers is preparing for March 14th with the focus of a military operation. Michael Zeiler runs GreatAmericanEclipse.com, a site dedicated to eclipse mapping and education. He's been coordinating with hundreds of observers across multiple continents to ensure maximum coverage. This is the eclipse I've been waiting for my entire career, he told me. I've photographed 11 total lunar eclipses. None of them come close to this. I've got 6 cameras set up at different focal lengths, all programmed to shoot continuously through totality. If clouds take me out, someone else in the network will get it. Dr. Paul Maley, a retired NASA engineer who has observed over 80 solar eclipses and countless lunar eclipses, is setting up a live stream from Tenerife in the Canary Islands, one of the best locations for dark skies and clear weather in the eclipse visibility zone. The key is to capture the transition, he said. Everyone will photograph maximum eclipse, but I want the 2 minutes before and after when the moon is sliding in and out of the deepest shadow. That's where you'll see the darkness gradient. Astrophotographer Andrew McCarthy, known for his hyper-detailed composite images of the moon, is planning something ambitious, a time-lapse composite showing the moon's brightness change throughout totality, with surface detail extracted via image stacking. If I can pull enough signal out of the data, I want to create a single image showing how much darker the center of the moon gets compared to the limb, he said. No one's ever imaged that before because no one alive has had the chance. And then there's the crowdsourced observation campaign being organized by the Astronomical League, a coalition of 240 amateur astronomy clubs across the U.S. They're asking members to visually estimate the moon's brightness during totality using the Danjon scale, a 5-point brightness index developed by French astronomer André Danjon in 1920. The goal is to collect hundreds of independent observations and compare them to the 1877 reports. "We want to know if the 1877 observers were right," said League President Carol Eorg. "They said the moon was barely visible. We want to quantify that. Is it a Danjon L equals 0, completely dark, or an L equals 1, where you can just barely make out surface features? No one's measured a central eclipse in the modern era. This is our chance." These are the people who will document the darkness, not the institutions, not the agencies. Individuals with telescopes and passion and the understanding that this moment won't come again in their lifetime. You need a plan. Here's how to see this. Step 1, check your time zone. The eclipse is timed in UTC. Convert it to your local time. Maximum eclipse, the deepest point, is 6:58:14 UTC. If you're on the US East Coast, that's 1:58 a.m. Eastern Standard Time. US West Coast, 10:58 p.m. Pacific Standard Time on March 13th. London, 6:58 a.m. Greenwich Mean Time. Paris, 7:58 a.m. Central European Time. The full eclipse is visible from the Americas, Europe, Africa, and Western Asia. If you're in East Asia, Australia, or the Pacific, you're out of luck. The moon will be below your horizon. Step 2, get to dark skies if possible. The darker your sky, the more dramatic the effect. Light pollution will wash out the dimmer phases. If you're in a city, get to a park. If you can, drive 30 minutes outside the urban core. The difference between magnitude +3 and magnitude +5, naked eye visibility is enormous. Step 3, let your eyes adapt. Don't look at your phone during totality. Don't use flashlights. Your night vision takes 20 to 30 minutes to fully develop. If you kill it with white light, you'll miss the faintest stars appearing around the darkened moon. Step 4, use binoculars or a telescope if you have them. Even a cheap pair of 10 by 50 binoculars will gather enough light to reveal surface detail during the darkest phase. A small telescope will show craters even when the moon is magnitude +4 or dimmer. You don't need fancy equipment, you just need glass. Step 5, look for stars. During maximum eclipse, stars near the moon will become visible. Regulus, the brightest star in Leo, will be about 8 degrees west of the moon. Spica, the brightest star in Virgo, will be about 15 degrees to the east. Under truly dark skies, you should see stars down to magnitude +6, meaning the Beehive cluster in Cancer could become faintly visible to the north. Step 6, take a photograph, even if it's just with your phone. You won't get detail, but you'll document the moment. Set your phone on a tripod or stable surface. Use the longest exposure you can without star trailing, usually 2 to 4 seconds, and shoot in RAW if your camera app allows it. You can pull detail out of the shadows in post-processing. And most importantly, look with your eyes first. Don't experience the whole thing through a screen. This is a once-in-your-lifetime event. You can photograph it for 30 seconds and watch it for the remaining 17 minutes and 30 seconds. Let's talk about what comes after. The February 18th, 2172 eclipse, the next central totality, will be even deeper than this one. Eclipse magnitude 1.931, with the moon passing just 22 arc seconds from the shadow axis. Maximum totality will last 19 minutes and 8 seconds. It will be darker than March 14th, 2025, darker than March 3rd, 1877, darker than any lunar eclipse since the year 1544. No one reading this will be alive to see it, but someone will. A child born today will be 147 years old in 2172, impossible by current life expectancy, but perhaps not impossible by 2172 standards, medical advances, life extension technologies, cellular regeneration therapies. Who knows what will be available in a century and a half? Maybe someone alive right now, someone in a hospital nursery at this very moment, will live long enough to see both eclipses. More likely, the people who watch in 2172 will be separated from us by the same unbridgeable gap that separates us from 1877. Different technology, different society, different problems, but the same moon, the same shadow, the same geometry clicking into place with mechanical indifference. The moon doesn't care about human lifespans. The orbits don't pause for generational memory. The dance continues whether we're here to watch it or not. But we are here, and it's happening next week. There's a specific kind of weight that comes with witnessing something no one else alive has seen. It's not just rarity. Rare things happen all the time. It's the knowledge that the continuity of experience has been broken, that the thread connecting you to the last observer snapped decades before you were born, that you're not inheriting this moment from anyone. You're rediscovering it. When you look up on March 14th and see the moon darken to that charcoal gray, you'll be seeing something that exists only in fragmentary written accounts and 3 blurry glass plate photographs locked in an archive somewhere in Maryland. You'll have more in common with the 1877 observers, scattered across continents, staring up with primitive instruments, trying to make sense of the darkness, than you will with anyone else alive today. And then it will end, the moon will brighten, the stars will fade, the sky will return to normal, and the countdown to 2172 will begin, with you on the outside of the window, part of the generation that watched and died before it happened again. This is the price of cosmic timescales. The universe operates on rhythms that don't sync with human lives. We get fragments, glimpses, single moments of alignment that we either witness or we don't. There's no replay, no second showing, no director's cut. On March 3rd, 1877, an unnamed observer in Lahore looked up and described the moon as a hole in the sky. That phrase survived 147 years because someone wrote it down. What will you write? What will you remember? What evidence will you leave for the observers of 2017 that you were here, that you saw it, that you understood what you were looking at? The moon goes dark in 7 days. Everyone who last saw this is dead.